Hey, so let's do some warm up first, right? Let's do some warm up. Let's try and solve this question. I spent about 5 minutes. See what you can work out with this exercise here. Find the volume of the solid that lies under the paraboloid z equals to x squared plus y squared and above the region D in the xy plane, bounded by the line y equals to y 2x and the parabola y equals to y squared. So the picture here is what? So the picture here is depicting the normal, the domain. Okay, the domain of your function. So your function is what? Z equals to x squared plus y squared. Okay, so this surface here lies in R3. Okay, fxy equals to x squared plus y squared. Okay, and then you want to find the volume that lies under this paraboloid here. Meaning what? You need to find the double integral. Because x squared plus y squared is always greater or equal to 0. Okay, so you need to find the double integral of this function here above this region. So remember how to integrate over general region or not? How to compute double integral? How to compute double integral? Fix one direction, right? So meaning what? You need to do the iterated integral here. Okay, so you need to do your integral as dx dy or dy dx, either one of them. Okay, and then you need to fix the domain here. Okay, does it make sense? Okay, so which direction you want to fix first? Maybe let's take one direction. Fix y first. Okay, let's fix y. Okay, fix y meaning we go to this the other picture here. So in exam, right, you need to know how to plot these y equals to 2x line and y equals to x squared line. Okay, and then you need to know how to find the intersection. Is everyone clear about doing this? How to find intersection? So you need to equate two equations, right? So in this case, you have 2x equals to x squared. So the two intersection points are s equals to 0 and s equals to 2. Okay, and then you plot into your curve, find the y value. Right. So if we fix y, so in this diagram here, y is going from where to where? 0 to 4. Okay, going from 0 to 4. Okay, but how to determine your x? Let's see. So if you fix your y at 0, you say y is going from 0 to 4, right? So you need to tell me what happened when y equals 0. Y equals to 1, 2, 3, 4. Okay, so when y equals to 0, what is your x? Your s is just 0. Okay, but when you go to 2, for example, what happened? It's between 1 and square root 2. Okay, 1 and square root 2. So let's put this out. 1 and square root 2. So it's here, 1 and square root 2. Okay, and then, but if you go to 4 again, it becomes a point again. Okay, so how we describe this? So how do we describe this? So that means when you change to different y, your s changes. This means what? S is in terms of 1. Okay, so you need to find this line in terms of y. Okay, find the other upper bound, x in terms of what y. Okay, in terms of y. So x is bounded below by y over 2. Okay, and then bounded above by square root y. Okay, so this is your integration domain. Yeah, 12 y here, square root y. Okay, so you can write down your integration domain here. So I fix my y from 0 to 4, and then I fix my x1, half y to square root y. Okay, so think about this. Does this iterated integral make sense or not? Does it make sense? You integrate x with respect to, you integrate a function with respect to x first. Okay, but your x is depending on y. So you will left everything in terms of y. And then you integrate the function y in terms of y. Then you get the answer. Okay. All right. How about the other way? What if we do the other way? What if we fix x first? 0 to 2, right? Okay. So how to get this 0 to 2? You need to check your intersection point. Okay. Make sure you get the intersection point, right? And then how about y? Bounded below by x squared, bounded above by 2x. So you need to make sure that you plot this curve right, okay? If you plot 2x below, plot x squared above, then you will be in trouble, okay or not? So you need to make sure you plot the right number, right region, okay? So how to check whether 2x is higher than x squared or not? Just plug your value. Just plug value and try. Try a few values, okay? Yeah. Okay. So try and compute the integral, whichever method you want to use. Let's see we all get the same answer or not. Just try any direction you like. Do both if you like. If any one of you finish, just shout out your final answer. Ethan, you done? What do you get? Hmm? Too ugly? Yeah, correct. Mathematics should be beautiful. Truth and beauty is a math. Hmm? You have finished? There's a chat here. Let's see. Any answer from online or not? Yeah. So what's that? 32/7. Which method you use? Top or bottom? Use the 23, 32/7. How about the others? Huh? How about the others? You use top or bottom? Bottom also. What do you get? 35. Okay. How about the others? Any agree answer or not? You try and compare again. Ethan, eh? I thought Ethan finished earlier ago. Which one? Okay. I think there's one correct answer here. Anyone got the same? Vincent, you got it? You haven't finished compare? You got the first answer. Okay. Use the top. Hmm. The down one is 7. Oh, then what's your numerator? What do you mean by complex? How complex? Really big? How big? What? How long? 6 terms. Wow. Maybe tell me the 6 term. 6 term or 6 digit? 6 digit. Yeah, what's the 6 digit? Oh, oh, okay. Then you need to expand it. You need to finish expanding it. Yeah, you need to expand it. 648/185. You change your answer again. 618 over 648. Yeah, 对对对，I'm agreeing. Yes. 216/35. You also get 216/35. Okay, yeah. So the correct one is 126/35. 216/35. Yeah. For both of them, you should get the same. Okay. Others will got it. Manage to get it. Mm-hmm. Yeah. Make sure you are okay with the polynomial integration. These are just polynomial integration. Okay. Others manage to get or not? 216/35. Okay. Okay. Anything to ask about calculation or not? Do you want to try one more example, or we're okay to skip to next part? Can skip? Confident? Two more example I leave for you to do yourself. Because last time we skipped 3, right? Yeah. Or next week or next lecture do one more again. Okay, depends. Okay. Okay, maybe we'll come back. So let's skip first. Otherwise, you try and do yourself for these two. I think we will meet again this prism in the vector calculus. But this one you should definitely try. This is very similar to what we did just now. You should try it. Okay. And then this you can try as well. Otherwise, we'll try next lecture. Okay, so let's continue with where we stopped last time. So we stopped at this polar rectangle here. So how should you think about polar rectangle? So one type of polar rectangle is just a circle. Okay. In general, it is like the pineapple slice inside your burger. Okay. We can take out the middle circle from the outer circle. Okay. Does that make sense? So you can imagine you have a list, okay, and then I can take out the inner disk. Okay, so I build an annulus. So what I mean by annulus is I have this, okay, right. So let me make it rounded. Okay, so this is my disk. Okay, so this is one type of polar rectangle. And then the other type of polar rectangle is I can take out another circle within this circle here. And then this is what we call the annulus. Okay. If we don't consider the full angle from 0 to 2 pi, we will cut it as a sector length. Okay, the sector of the annulus. So if we don't consider the full angle, so a circle is angle from where to where? From 0 to 2 pi. Okay, so if we start with 0 and then we cut a certain angle here, then we will get some sector like this. Does that make sense? So this is the most general polar rectangle you could get. Okay, make sense or not? So I mean, I could cut this pineapple slice from a certain angle here. Okay, and then I can get just the sector of it. Make sense? Okay. So there are two. Okay, there are two similar to xy. There are two variables to control here. So what's the two variable in polar coordinate? Is the radius and the angle. Okay. Both of radius and angle are computed from the origin. Okay. So area, the radius is going from 0 from the origin to infinity. Okay. And then how about angle? 0 to 2 pi. But where I start? I start with the positive x axis. Okay, I start with the positive x axis. Okay, 0, then go around 2 pi. So 0 to pi is where? From the positive x-axis to the negative x-axis. 0 to pi, for example. Half of it. Make sense? Does it make? Okay, let's look at some example or theory first. Okay, so how to compute the area of this slice here? You know how to compute the area of this slice? So area of a sector is what? Let's say this angle is theta, right? So area of a sector is what? Half r square theta, right? Half r square theta. Why? How to get this? You remember? Area of a circle is pi r square, right? Then you need to take theta over 2 pi, taking the ratio. Okay. So this 2 here coming from the 360 angle, 2 pi in radian. And then theta here is the ratio. So this one is the full circle. Then this is the ratio, depend on the ratio of the angle you make for the center. Does that make sense? Yeah. Okay. Okay. So how about this area here? How about this sector here? This is a cut off sector, right? So we take off the inner circle here. So we need to take away the smaller sector. So we are doing half. Let's say the radius here is b squared. Okay. And then we have angle beta minus alpha for the inner for this angle here. So let me label it. So this angle here is called beta minus alpha. So you need to take the outer sector minus the inner sector to get this cutoff sector here. Okay, does it make sense? And then we can rearrange the term here. Okay, we can factorize beta minus alpha out. Okay, and then we can rearrange. So let me do it for you. So let us pick up the beta minus alpha term. Okay, and this part beta minus alpha here is what? Is the change of angle. Okay, from alpha going to beta. Does it make sense? From alpha going to beta. And then how about how to discuss about this number here? B square minus A square. Difference of 2 square. Okay, so what we do is we split this into 2 terms. So B minus alpha, so B minus A, and B plus A. B plus A over delta theta. Okay, and then we combine B plus A over 2 together, and B minus A together, and then delta theta. So what is B minus A? So B is the outer radius, A is the inner radius here. Okay, so B minus A become a change in radius. Okay, so this part we make it a delta radius. And then B plus A over 2, they make it R bar, which is what we call the average radius here. So what is this about here? So this part is something to do with the double integral. Okay, so this represent, okay, this represent an area of a sector. So it represents the area of a sector. So when we integrate over the polar rectangle, we have an extra R contribution here. Okay. In later course, you will learn why this R pop up. But for now, you should remember that there's an R contribution to my area of the polar rectangle. Does that make sense? So when you do polar integration, you need to remember that you need to multiply by an extra R. Okay, R dr d theta, not just dr d theta. You need R dr d theta. Okay, in future we'll learn how this R pop up. But for now, the concept is for the area of a polar rectangle, you need to take into consideration the factor of R. Okay, R times the change in R, change in theta. Okay, so here become R dr d theta. Does that make sense? Mm. For future, we'll do this more formally, more formally. But for now, please accept when you do polar coordinate, you need to multiply by now. For future, we'll see how this pop up. We need to introduce some more gadgets to talk about this. Okay, hold on. Okay, just remember when you do polar coordinate, make sure you multiply by R. Okay. Okay, let's do example, right? Let's do example. Should we go through this picture next time maybe? Okay. So let's do one example here. So evaluate this function, okay, with respect to some area. I didn't tell you where this area lies. Maybe using xy plane or polar. Okay. And then over the region R. Okay, what is this region R? This region is the upper is in the upper half plane, bounded by circles, two circles. Okay. You know what these two circles represent? What's this two circles represent? No, I mean these are circles, right? What kind of circles? You see, they are equaling to different number there. Right? So one is radius one, the other is radius two. Okay, but where's the center? Origin. Both of them are in the origin. Okay, so we try and draw this region out. So let's draw this region. So first of all, you have a circle, right, with radius 1. Okay, center of the origin. Then you have another circle, yeah, with radius 2. Okay, so where's the R here actually? Where's R? Upper half plane, so on the above x-axis. And then bounded by these two circles. So meaning is the annulus in the middle here. Okay, half annulus. So half of it. So here is your R. Okay. So let's get for R. Okay. Yeah. It doesn't want to give me back my circle. It doesn't want to give me back my circle. Okay, so let's draw the R out. So here is your R. Okay. All right. So how to integrate this? Do you want to do xy coordinate or not? If you want to do xy coordinate, what does it mean? Let's say we do dy dx. So you need to check where's your x going. Yeah. So where's your x actually? Let's determine it. What do you mean half? Hey, this is a good question Lohao asked last time. Wait, later I will address this. Let's plot this point out first. Okay, so here is 1, here is 2, here is -1, here is -2, here is 1, here is 2. Okay, I plot all the point out already. Okay, so let's do my question first and then later address what the Ethan said. So if I want to fix dx dy, meaning what? I need to integrate from -2 to -1 and then 1 to 2. And then what? Actually, your x is going from where to where? -2 to 2. Okay? But your y is bounded by two different circles again. Does it make sense? Okay, so okay, let me write out. Let me write out. Okay, so if we do the original traditional way, so do the xy way. So my x is bounded by -2 to 2. How about my y? Bounded below by what? So this curve is what? 1 minus x squared, 4. 4 minus x squared equals y. Okay, this is the outer one. Okay, maybe we use different color. So this is the outer one. How about the inner one? Y equals to square root 1 minus x squared. Does it make sense? Does it make sense to everyone? The top one is square root, positive square root, right? But the bottom one is negative square root. Okay or not? Okay. 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 All right. Okay. So how should I determine my y here? My x is going from all the way from -2 to 2, but how do I find this line? Right. Y is going from where to where? Y minus x squared to square root 4 minus. Let's check whether this is true or not. Check that this is true or not. If my x is 3, 1.5, for example, right? Is this function defined or not? No, right? So this part here is what? So you should see that, you see. So I slice my function like this. Slice my region like this. Correct or not? Yeah, so x between -2 and 1. What is the lower bound? Lower bound is this line. X equals to y equals to 0. Okay, so let me write down. So when you do integration, right, from -2 to -1, your y is bounded above by square root 4 minus x squared, bounded below by 0. Does it make sense? Does it make sense or not? So I should cut like this for you. Let me cut it. So let me cut it. I should cut like this. Okay. Think good not got a new function now. Let's do it. Like this. I break this picture into 3 regions. Can you see 3 regions here? 1 part, and 3 part. Okay. And then this 3 part here, for -2 to -1, it is bounded above by the outer circle with bounded below by this horizontal line. By between -1 and 1, it is bounded above by a larger circle, bounded below by a smaller circle. And then similarly for this part here, you are bounded by x equals 0 and then the larger 0. Does it make sense? Make sense or not? You can see how to break the region. Right? Okay. We cannot just use a single region, a single equation to bound because there's no circle here in this part. This part is a horizontal line. Horizontal line, x equals to 0. Sorry, y equals 0. Okay. So there are 3 integral you need to do. Right. So f dy dx, f dy dx plus from -1 to 1, which is square root 1 minus x squared, square root 4 minus x squared, f dx dy. And then plus from 1 to 2, from 0 to square root 4 minus x squared again, f dx dy. Okay, does it make sense? So then you need to compute this. And you need to go through this whole step here. Everything here. You have square root involved in your calculation. Yeah. And then I think this step is kind of hard because you will get some pi out from the first square root integration. Right. Okay. We want to avoid this mishap here. Okay, we want to avoid this by just doing polar integration. Okay, we don't want to go through this many integration here, all the square root thingy. Okay, we want to pass by all the square root calculation. How to pass by? We use polar. Okay, let's use polar area to understand this question here. Okay, so let's scrap this guy out. So if I understand this as polar, can you see how we explain this region using polar? It is bounded by 2 circles, right? Meaning you take the large this, take away the small this. Okay, so instead of x and y, we need to determine where is my r, where is my theta. Okay, so my radius is going from where to where? What? Huh? R1 to R2, yes, correct. So where is my R1 here? 1. Where's my radius? 2. Okay, how about angle? From where to where? Positive x-axis to negative x-axis, which is going from 0 to pi, just pi. Then you need to write down your uh, double integral in polar form. So integrate the r dr d theta. Okay, you got an extra r. But in the middle is 3x plus 4y squared. How to go from x, y to r theta? Still remember now. S equals to r cos theta, y equals to r sine theta. Okay, so you need to sub this value in. So it becomes r x times r cos theta plus 4 times r squared sine squared theta. Okay, and then integrate r first, so r is from 1 to 2, and then theta is from 0 to. Okay, so my integral become double integral become the double integral in polar form. So do you understand why now we put a here, dA here? Because we can change our coordinate. If we use dx dy to be what we did before, but if we change to dr d theta, then we'll drop an extra factor r. Okay. Let's see. So do you want to try and compute this? Yeah, try and compute this integral here. It shouldn't be hard. Yeah, try and compute this integral here. Try and do it. Let's do it. So it's the same. Okay, when you integrate with respect to r, you treat theta as a constant. Okay. Let's do it together. You could check if we got the same answer or not. You get the same integral? Same? What's the answer you got? Do not compute. Have to compute answer. Fifteen over 2 pi, yes, correct. Okay, 15 over 2 pi. So everyone should get 15 over 2 pi. Yeah. Yes. Okay. You should get 15 over 2 pi. Okay. Of course, you could imagine that you cut in the x direction, right? You can fix y first and then cut in the x direction. Okay, you could do that as well. You can do that as well. All right. Then you can do that as well. So, how many region you think if you do this way, you need to cut this shape into? Let's say I fix y, okay? I do the x integration, right? So how many region you need to split? What do you think? How many region? So just now, okay, just now when we do the xy double integral, right? We fix x first, and then we do the y direction. Okay, how about if I do the other direction? I fix y first, and then I do the x direction. How many region I need to split into? What do you think? Two. Actually, you also need three. You also need three of them. Okay. Yeah. You also need three of them. So these are the three regions I got here. Yeah. So these are the three regions I got here. From 1 to 2, I have one region. And then 0 to 1, I have one region. But two regions on 0 to 1. Because okay, let me remove this and then I draw it to you. So if you look at this shape, right? So if I cut along this way, so if I cut along this way, 1 to 2, then you have one region top and then two region at the side. Does it make sense? Does it make sense? Okay, I have one region at the top and then two region at the side. Okay, if I do it this way. Okay, does it make sense? If you cannot understand what I said, right, I urge you to try yourself. Okay, try yourself. It's okay if you don't complete the calculation. You can refer to my calculation. Okay, but you need to try to cut this. It's a good exercise that to cut this picture in everywhere you can. Because in future, when we do vector calculus, you need to learn how to cut the surface or the solid. Is it okay? So you need to make sure you know how to cut these 2D surface at least. Okay. All right. So let's go back to the intern question, okay, which is also what Lohao asked last time. So you can see that this shape is very symmetric, right? Symmetric or not? Symmetric, right? Seems like I just calculate this side multiplied by 2. I can get the whole double integral. Is it true? No. Why is it no? The question is your question, right? So the question is, since this domain is symmetric, why not I just compute half of it and then multiply by 2 to get the whole integral? Is that your question? Yeah. Yeah, that's your question. Correct or not? See, this domain is so symmetric, right? I can just split it half and then compute half of it. So in that case, I get radius from 1 to 2, but my angle from 0 to pi over 2. And then the integral, I just multiply by 2. I get the whole thing. Is it true? Believe or not? Believe 啊，若然表示同意。Okay. Not always true. Why is not always true? You need to know that why are you computing? You are not computing the area. You are computing the volume. Where's the volume? The volume is living at the top here. Okay or not? The volume is living at the top. So it is just here, region. So you should imagine something like this. You see? So here, please imagine here as your domain. Right, this flat surface here. Symmetry or not? Is this symmetry? Rectangle here, cut it half. What am I doing? I have a surface at the top. If my surface like this, there's no symmetry already above this domain here. If I split into half, you can see that the right side here will have smaller volume than the left side. Okay or not? You cannot just see the symmetry in the domain. You need to see the symmetry of your surface. Okay? Can you imagine? Can you imagine or not? Can you imagine? Right. So if I cut half, see, this side will have more. This side will have less. Okay, so you cannot just look at the symmetry on your domain. Okay, you need to, it depends on your surface. Okay, clear? Everyone clear? Clear now? Any question? More question? Ethan? Okay. Area is because you just look at the, I mean, if you integrate with respect to one variable, let's say, right? What you do is what you draw is really what you're computing. But now you still have volume on the top here. You haven't drawn it out yet. Yeah. So it doesn't represent what you calculating. Okay. This is just a domain picture. Always you will see me writing here, domain. So that's why I don't want you to confuse with the domain and the graph of the function. Right. This is just a domain function, the domain picture. For the graph, I need to draw a third axis. Okay. I need to draw a third axis. Okay. So always you will see me writing there domain. I need to remind you this is just a domain. I haven't mapped it yet. Okay, I haven't tell you what the surface look like on the top. I haven't tell you what's the slice, how the slice sit in R3. Okay, I need to tell you how the slice sit in R3 if I'm gonna draw the graph up. Make sense or not? Okay, okay. What's next? Okay, let's try one more exercise before we take a break. Okay, let's try this exercise before we take a break. Find the volume of V of the solid bounded by the plane z equals 0 and the paraboloid z equals to 1 minus x squared minus y squared. So this graph is a domain graph, is a domain or a whole graph? This graph here is a domain or a whole graph? Huh? Is a domain graph or the graph of your surface? Which one? Graph of your domain or graph of your surface? There are how many axes here? 3. 3 axes here. R3. So graph of F live in R3. So this thing that bulged up is the paraboloid we're talking about. Okay. 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 So you want to find this volume. How to find this volume? So the volume of this is what? From this picture, you can see that this surface here is always greater or equal to 0. Okay. So we have a D of Z dA here. So we need to determine what's your D. What's our domain here? We integrate what domain? Can you determine what's the domain here? Circle. Okay, seems like a circle. So what's exactly the circle is? How to find it? Okay, so you set your Z equals to 0. Okay, because it is bounded by the plane Z equals 0. Do you know where's the Z equals 0 plane or not? It's the XY plane. XY plane has Z value equals to 0. Make sense or not? 110, 210, where are they? They are on the XY plane. Okay. Okay or not? So I think I should draw some more to make you imagine what's going on. So let's say this is a R3 with X, Y, Z, right? So here's the origin. Where is Z equal to 0 plane? It is the middle part here. Okay, it's the middle part here. Yeah, no? Make sense? Okay. And then we need to find Z equal to 0, find the D. Okay. So what is D? D are all the xy point in R2 such that 1 minus x squared minus y squared is less than or equal to 0. Okay. All the thing inside your circle. Make sense? Okay. So the outer layer here is x squared plus y squared equals to 1. And then I include everything inside. Okay. So how to integrate this? So you want to use polar coordinate or you want to use rectangular coordinate? Both. Mm. Mm. Let's use the, okay, so wait, let me draw one more picture here. So what's the domain picture here? Okay, so the domain picture is like this. What is the D here? Okay, so I look into here, what is it? Okay, I look into here, what is it? So I draw it up, X and Y, and then I have a circle centered at origin, and then the radius is 1, and then I include everything inside here. So this is my D. Okay. Okay. Okay, no. So this is the domain picture here. So I got minus 1, 1, 1, minus 1 here. Okay. You could do dx dy. Fix your x and then calculate what is 1. Or fix your x, calculate what is y. Fix your y, calculate what is your x. Okay. But if you do that, this is circle, right? You have to describe your curve in terms of square root. Okay. So square root in integration is very troublesome. Okay, we want to avoid it. So we will use polar. Yeah, we will use polar. So how to make this polar? So how do you describe this region using r and theta? R going from where to where? 0 all the way up to 1. Angle from 0 up to 2 pi. Then you can draw this domain. Okay. So the radius are all the point from 0 up to 1, and angle is from 0 up to 2 pi. Does it make sense? Make sense or not? Does it make sense that these two set of inequality will give you all the points inside the circle here? Does it make sense? Radius all the way from 0 to 1. And then you swipe up all the points from theta equals 0 all the way to 2 pi. Okay, so you swipe out this. Make sense or not? Okay. Okay, if this makes sense, so we need to integrate over the polar rectangle here. So going from 0 to 2 pi, 0 to 1. So my surface is 1 minus x squared minus y squared. R dr d theta, very important, multiplied by r. Can you do integration now or not? Can do it now? Not yet. How? What you need to do? You need to change your coordinate. Okay? So s squared plus y squared equals to r squared. Okay, in the coordinate change. So you get 1 minus r squared. R dr. Okay. How to get this? S equals to r cos theta. Y equals to r sine theta. So s squared plus y squared become r squared. Okay, because cos squared plus sine squared is 1. Okay, then do this integration here. Okay, do it. Let me know what you get. Do this integration. R minus R cubed. Do this integration. So the punchline here you need to remember is you need to multiply by an extra R when you do change of variable. So you can see that in this case here, right? This paraboloid is quite symmetric. Maybe you can split this, Ethan. Maybe you can split this into quadrant and then multiply by 4 and see if you get the same answer. Yeah, it seems symmetric here. So you could, in principle, split into 4, divide into 4, and then just compute this quadrant and then multiply by 4. You should get the same answer with this. What's the answer? Power 2. Okay, good. Power 2. Actually, this there's a fast way to calculate it, right? Any one of you split this integral or not into a product? Because there's only one function, okay, there's one function with respect to r, but it is not composite with theta. So you can split it into 0 to 2 pi of d theta, and then 0 to 1 r minus r cubed dr. Like this. Do it the same time. Okay, because you can write it as a product of different variable. Okay, so you see, last time we talked about x, y, right? So it really doesn't matter. Okay, it doesn't matter. Whatever you put there. Okay. Okay, everyone should get pi over 2. So, Chen Jack, can you do the rectangular coordinate for us next time? Try at home and then tell us next time. Or you send it to me and then I'll show the rest. Ethan, Ethan, want to divide this to 4 and try and compute. And then you send us the result also. Instead of going from 0 to 2 pi, try and go from 0 to power 2. You should get pi over 8. Yeah, try and find it. Okay? Yeah, so I'll get 2 solutions from you guys. One from Chenjet, one from Ethan. Okay, so far any question about this polar rectangle? Any question about this here? Any question about this solution? No question. If no question, then we will take a break until 4:40. 14. 14. So 有没有
你应该把一个烟先挂在你的，外面那个本来不代表你应该。哦，对，大概。
有些是什么来？
我的理解是两种都有好的，一个不能用好，另外一个
然后，然后还有那个 minimum spend 这个拉呀，在我这里花了，哇，我的天呀，这个真的我的那个，那个我们可以保证你买到点对哦。然后最大化 voucher 有些是非你可以用，现在你可以用，有些是 COD 可以用，
也有那些东西。然后对 COD 那个我也是有什么东西。它有些可能扣到90%，它是能 cap and 反馈起来。这我没有看OK，有这样的东西有吗？有包车先吗？不然你没有这样，不太多。
我年
说你看又有这个 cashback 算是说你还把你看对。然后它会有不同的，比如说28%啊，可以更少或者更多，可以讲。然后有时候它会换不同的 spend， 会有几个 variable 在这里面，你可以 fix 一个，然后再讨论哪一个比较划算，哪一个比较值钱。然后它不止 cashback， 有时候是 coin back。所以 coin back 是什么意思？其实那个也是你的钱来的，但是它把你的钱加上一个时间。因为 coin 呢，你要在3个月内没有掉，不然就没有。所以你是说 coin back 是什么意思？它把你真钱换去 coin， 加上时间，把你钱变成有时间钱。
随着时间变少
，3个月过后你的 coin 就不见了。所以说你3个月
少，3个月越
不是越来越少，就不见，你没有用就是他的了。其实你已经还了那个钱。如果你3个月内不用那个 discount 就不属于你的，因为被他吃掉了，所以你还是用原价嘛。所以你除非你要用那个 coin 才可以赚到它的东西，但是你要用它的 coin 的单额，你又要用包车，又要有 minimum spend， 然后就一直 spend 下去，它就是这样。所以我们要怎样买多少一个包车里面，我们要买多少钱以内？我们才赚到那个它的点
连续的连续使用的那个包区
都可以，什么情况都可以。我一定要赚到他的钱。
有些店是你吃了过后还是给你包区，然后你用那个
没有，我们在讨论小币，而且他说很快。对，还有一个是我也不知道那个多，我不知道在哪里找。我是 try， 它有说对，它一个 product 只可以扣最高3000 coin 吧，最高了3000吧OK 3000 coin 代表100 coin 代表1块钱，所以3000 coin 代表30块。你最多能够用在一个 product 上面，一个 product 上面是30块。然后我也不知道它的那个 percentage 怎样算，如果你找得出的话也可以。based on 多少钱？可能10块钱，他不可能给你扣30块的嘛，他给你扣可能1块2块，我不知道，不一定，他可能跟 product， 可能跟商店，我也不知道。如果你找得出也可以，你明白吗？
我要找扣多少钱啊？
没有啦，我讲了这么多东西啊，看你要做什么就去做。这些我都很懂。
我觉得比较评论的就是哪个组合这样子比较。
也可以哪个组合，所以它既有2个组合。它第一个是 shop voucher， 它可以 apply， 就是那个你买那个东西，那个商店会给你一些 voucher， 它会扣了过后，不是你还可以再扣一个 shopping voucher， 只有这2个你可以用到 shop voucher 跟 shopping voucher。shopping voucher 它这样多扣法，你只可以选一种扣法，所以亚马逊比较惨的是 free shipping， 或者他讲的什么 COD cash on delivery， 就是如果你选项你要单套，还有一个 SPAY 的然后对，真的是可以看的。很多嘛，加盟我跟你讲，他把人搞到可多，人家就是花钱嘛。
对啊。 我们是数学家，不可以给人家骗。对对对，I mean，对对对，而且那个组合很危险，你知道吗？组合，因为本来你可能是80块我买嘛，我可以用的，结果他 shop 包车一进来啊，变成75块，这样你就不能用那个最大化的 discount 包车了，你知道吗？
不会有这样
啊，因为他是先扣钱，shop 包车先把你钱扣掉，把那个 product 钱扣完了，你才还那个钱，然后你的 shopping 包车才扣那个。
比如说你个手机给你个80块，你们先80块的那个网车，然后就给你一些 cashback 这样子的。然后你要买的那个口袋，那个 shop 是给你可能是9块的，然后他那个口袋本来是80块的，他扣完那个10块，
变后排了，
变成75块，
那你没有明天分用。假设你在冰冰的 shop 买东西买5块的话，不一样 shop 啊，你又要还 shipping fee 了。
对
，shipping fee 是在最底下层，它没有扣在这种。对，讲我要不要再加多5块买下去呢？
是那个秀的那个保就是可以不用弄掉，就是讲那个
可以把秀包车弄掉，所以你要决定我要不要弄掉这个秀包车，这样咯。我能不能赚更多？如果我去掉这5块钱，我的那个几八仙可以帮我赚回这5块钱。很多次。
很多都是讨论哦，
非常讨论的。那都有来个最有趣的来讨论。
也是这个最好用。对吧？用的。
哎，做什么？你喜欢什么先？你无欲无穷，去量一下无欲无穷在哪里？我知道，我知道，我知道。可以啊，对啊，我就可以啊，对啊。你的那个圈圈应该跟现实生活中有关系啊，比如说那个花。OK， 玫瑰是其中一个。你知道肉植物吗？肉植物知道吗？现在最近很多人种多肉啊，另外一个名字是多肉植物，那种很小的，小小一朵，小小一朵。我看一下有没有照片，我家里有一个，它的叶子生到很喜欢，因为它就很肉。你看到什么你就觉得它很肉吗？
甜啊，很甜蜜。它是啊，对，它叶子是肥肥。哦，这样我应该有印象，我应该记得。那你要开灯在一些情绪会去种我的话，我们 QQ 有，不然我拍了发现，它叶子也是这样子生出来的。对啊，方面还可以讲，方面还可以讨论一下这个。来个，对，我这边不懂。也考虑到一个有没？他有跟那个有人做过 research， 你可以去找这样人家讲解。你去找在人家去哪看？能不能做一个速度记得什么时候速度对啊？就是说什么速度这样对省力啊。你可以猜啊，不知道是什么因素导致。我记得去年他们有做关于转弯的研讨，转弯的时候决定人家超越了，可能对你很有用。转弯少能决定超越了啊，测速度哦，就是他怎么在转弯处测是哪个？你不是直线两吗？然后拍它还是什么？转弯处嘛，他们把它 situation 放在云顶，讲 check 你去云顶的时候有没有超速？Okay, let's continue first. We will discuss
project again. So far there's 3 project with me now, I guess. Yeah, 3. So 4. 4, huh? Okay, 4. Yeah, but Jing already sent me the draft. I'll have a look. So you can also send me the draft. Hopefully I will get back to you your calculus project 1 this week. Okay, so that you can your feedback. So you should decide your topic by this week, and then you could hand me your draft weekend up to next Friday's presentation, right? Better before Wednesday, okay, or Thursday is okay because 6 pages. And then because it's the evening time, right? So by the noon of Friday, all of you should send me a full copy of your Beamer presentation. Okay, and then I will keep a folder. I'll give you a folder, and then you upload there, and then we will use my laptop to project your presentation. Okay. Yeah. Don't make too many slides. You won't finish it. 6 is the optimum pages. Okay, 6 pages. About 10-second each. You don't need to spend a full 2 minutes. On project is about 1 minute, and then on the 2 question is about 1 minute for 2 minutes. You don't need to use full 2 minutes. Okay. Make sure the things you say is clear in logic instead. Okay, not detailed instead, but clear. What's the outline? And then if people are interested during the Q&A section, they ask you what's the detail, how you compute this, then you can show them. Then okay, no need to show it at the first sight. The first sight you must be clear, simple. Okay, everyone should get it. Okay, all your classmates should get what you said. Okay, or not? This is doable because even the PhD thesis, PhD thesis is typically only one person will know that question only. And then you need to explain there's a competition, thesis competition, 3-minute thesis competition. You need to say your thesis in 3 minutes. Okay. Okay or not? Yeah. So I'll challenge you, okay, to say your problem and then how you solve your problem in 1 minute. Okay. So you have to make clear first slide, what's the problem you want to solve, and then the next few slide, what theorem you need to use to solve it. Okay, how you relate to calculus. Okay. Okay. Mathematical theory, how to use it in real life. Okay. One exercise I want you to check. So I'm not sure. Have you guys seen this meme before? This meme.
Oh.
Have you guys seen this meme before? Huh? No. But do you understand this meme or not? No. First integral. How to compare first integral? Substitution. Second integral? No elementary method. But today we're gonna integrate this. We're gonna do this set phase. Okay? We're gonna do this set phase today. Using polar coordinate. Yeah. Okay, we're gonna integrate this polar coordinate. So this is, I think you have seen this in your probability class. Okay, we're gonna compute this. That should be the music. All right, so let's do this. Okay, let's compute this. Actually, we turned out to compute this last semester because this is challenged by the probability lecturer, not the one you have now. It's Lin Tao Shen. Lin Tao Shen taught you guys before? Algebra 101 is what? Yeah. So he said, ask your calculus teacher, so it was me. So let's do it again. Show that this integral is actually square root pi. Okay. So how to do this? We're going to use a polar coordinate, but here there's only one coordinate here. How to make it a polar? Polar, you need 2. How to introduce another variable? How to introduce another variable? Huh? Any guess? Want to guess? How to make 2 variables out of 1 variable? Sure. Okay, we consider a product of 2i. Okay. Just now we split, right? Remember just now we split the 2 product if the function is not in composite of the 2. So we can split. So if we can split, we can combine as well. Right? We can combine this integral here. Make it into a double integral. This is a particularly nice double integral here because you have x squared and y squared. Remember, x squared, y squared is very friendly to polar coordinate. Because when you add the 2 squared together, you will just get r squared. Okay? So you get r squared. But what is this? How to change the integration domain? This is what? Negative infinity to negative infinity and then negative infinity to infinity. This is the R2 plane. Right, this is the R2 plane. The whole R2 plane. All right. So you make it into polar. Your angle is going from where to where? 0 to 2 pi. How about your radius? 0 to infinity. So you see, another advantage is there's 4 infinity here. You manage to reduce to 1 infinity. 3 of them become finite. Okay, no? Okay. And then e to the minus r squared dr d theta. Correct or not? Need an extra r. Okay, r. Okay. All right. What's next? Oh, what can we do here? Then what? Then your happy face appear again. Did you see your happy face or not? Did you see your happy face or not? Where's your happy face? Did you see your happy face or not? See the happy face? Differ by 2 is okay. I can create it. But R is very hard. Okay. But we got an R here. Now, right? See? See the happy face here. We got an extra exit outside. Okay. So meaning I can do substitution here. Okay, I can do integral by substitution here. So how to do integral by substitution? I let z equals to r squared. Dz become 2r di. And then r dr become dz over 2. Okay? Because when r equals 0, z is also 0. R equals to infinity, z is still going to infinity. Okay, so we keep the integration domain. And then we can take out my theta part first, okay? Because my theta is a constant function. And then my r become e to the minus z over 2. Make sense or not? Does it make sense?
This one how?
Which one how?
How the R turns to Z.
R to z. Integration by substitution. Is the happy face. Okay. Integration by substitution. And then there's nothing about theta here. So I can split the theta out again into product. And then for the r part, I just integrate e to the minus z over 2. Sense? Following? Okay. Okay, so the first part you get what? For theta part. What do you get? 2 pi. Okay. And then for the other part, what do you get? Actually, you need to do it as a improper integral here. Okay, you should do it improper here to be precise. Right? You only know how to do a definite integral. Okay, for indefinite, you need to use the limit. Okay, so what's this? So this is just A. What am I doing? Why I keep the whole thing? So let's make it like this one. And I can pull my 1/2 up, right? Because integral is linear, limit is also linear. Then I can pull it out, divide it. Then I need to do this integral here. Minus e to the minus z from 0 all the way to. Then I need to have a limit. Okay. And then what is this? Okay. Let's find out one more step. Minus e to the minus a plus 1. What is this? No, a going very large at the bottom. So you get 1 plus 1 is 1. 1 times pi is. So what do I get? I actually get I squared equals to pi. But I equals to plus minus square root pi. Can it be minus or not? Larry said cannot. No. Why?
Because
the initial term we got is E. Be careful, what kind of E? E can go bottom as well. Right. So what's the initial term? Let's recall. E to the minus x squared. So how to draw e to the minus x squared? At the top or at the bottom? E to the minus x squared, how to draw? Start from here to bottom. Right, because ex is like this. Okay, e minus x should swap. Because minus swap the sign. Does it make sense? Makes sense. Let me see, makes sense or not. Doesn't quite make sense, right? Because this is square. Yeah, square, what does it mean? Square meaning these both sides become same value. Right? Yeah. So this is not quite the picture. The picture, I think, is something like this. The two sides should be the same. This is an even function. Yeah, both going decreasing. Does it make sense? So the intersection is here is what? E to the 0. E to the 0 is 1. Okay? And then how to see this? How to see this decreasing? You should see that this is the combination of two types. So it's the combination of this one and this one. Okay, yeah. You take the tail of the. Okay, yeah. The color is too similar. So it's the combination of this one and this one. Okay. And then it says that what is this area here? This area here should be positive. Okay. So negative I is rejected because area under y equals to minus e to the minus x squared is positive. Okay or not? So this two decreasing is really crucial for this integral here. Because if we have what we have just now, it is diverging on one side. Then the integral shouldn't be finite. because these two sides here decrease fast enough, only this area converge to square root pi. Okay. Okay. So I guess this one maybe let's split it up. And then we say we can reject this guy. Okay. Make sense? Okay. Is there an assignment question on this one? I think there's one on this. I make you use the other coordinate to do it instead of this coordinate. Yeah. Do in the 3D. Okay. Yeah, but I asked you to do in 3D, right? So in 2D, you can use rectangle to fill your plane, or you can use circle to fill your plane. But in R3, how to fill your plane? Your box. Of course, you can use box. Use bigger and bigger box. What kind of object you can use? You can use sphere. Use sphere, the growing sphere. Okay. Or you can use cylinder. Okay, bigger and bigger cylinder. So these are called the spherical coordinate, cylindrical coordinate. Okay. Okay, so these are the where is it? These are the three objects we will use to fill our R3 later on. Not now. But I just let you know. Of course, you can use other coordinate, change the other coordinate to fill your space. Maybe ellipsoid or something else. Okay. Then these things will correspond to different change of coordinate. Okay. For example, xy change to r theta. How to change? X equals to r cos theta, y equals to r sin theta. Then here you need to do three variables. For example, for spherical, you need radius, you need two angle, for example. Okay. And then cylindrical, what do you need? You need radius, you need angle, and then you need height. And then rectangle is just x, y, z. And then how to go between these will be on the next topic. Okay. Okay. Let's continue with our polar region. Okay, so how about we have a general region here. So what does it mean by general region for polar? It means that you are no longer integrate over circle. Okay, your boundary here could be irregular. Okay, you see, your boundary here could be irregular here. Okay, it depends on angle. Okay, it depends on angle. It changes depending on the angle now. Okay. So you can see that on the angle side, it is constant. Okay. But when you change your angle, the other two boundary here changes based on your angle here. So the radius change based on the angle. It's no longer circle. Okay, it's no longer circle. Okay, let's see how we gonna deal with this case here. So for example, use a double integral to find the area enclosed by a loop of four leaf rows. Okay. And then give you this Rolle's equation here. Okay, you can use r equals to cos 2 theta to draw out the four leaf. Hope you haven't forget how to do this. Okay, so how to find the area enclosed by this loop here? It says area, but double integral compute what? Volume. So how to reduce the volume to an area? Remember? How to get the area of the domain from the volume? How to get an area of a domain from a volume? Still remember now? Huh? integrate over 1. So you should remember the example of a box. If a box height 1, then the volume of the box is equal to the area of your box. You just remember this. Okay, just remember this. The F here represents the extra height. Okay, you have to remember this. Okay, now the problem is how to determine this domain. How to get this domain here. How to draw this rows. How to draw the rows here. So this, first of all, this D here is controlled by two variables. Okay, R and theta. Okay, R and theta. So how do you control your R? Or rather, how to control theta first? Minus pi over 4 to pi over 4. Okay. How about theta? How about R? How do you find this radius here? What's this radius governed by? Cosine 2 theta. So it's bounded below or above by the function. So the radius is going from where to where? Bounded above by this gross here. But how about the middle point here? What's the least radius you can get? Yeah. What is the smallest radius you can get from this point? You touch the origin. So the smallest radius here is 0. 0 all the way, 0 from 0 all the way up to your rows. Okay. Up to your function. Okay. So all of them from 0 up to cos 2 theta. Okay or not? Does it make sense? Make sense? Okay, so once you get this, you are ready to do your double integral. So this represents your integration domain here. Okay, so you can do your double integral here. So let's fix from r dr d theta. Okay, so angle is going from minus pi over 4 to pi over 4, and then radius is going from 0 to cos 2 theta. Right? So you just integrate over r. Okay. So you could get r squared over 2 from 0 to cos 2 theta d theta, and then keep going path of cos square 2 theta. Sense or not? Yeah, because my r become r square over 2. Right? Then I cannot integrate power of square, power of cos, so I need to use the double angle formula. Okay, then now I can integrate this. Okay, and then what should I got? What should I have? What should I have here? You compute this integral. What should I have? What should I got here? What should I get for the answer? Yeah, try and compute. What should I get? Well, 8, yes. Okay, I should get power 8. Please compute it. Okay or not? Is it okay? How many? Okay. Let's see what's the next thing. Okay, we are going there soon. So let's you try this again for 5 minutes. We finish up this exercise and then we'll take a break. I try and do this. Maybe don't have the graph. Just look at these two equations. Find the volume of the solid under the surface inside the cylinder. How to do this? What's the domain? You need to find the integration domain. What's the domain you need to integrate over? What's the domain underlying here? Okay, you need to find it. What's the domain? Huh? Can you find the domain or not? Yeah, what's your integration domain here? Huh? Circle? Yeah, circle. Yeah, yes, right. That's right. Circle is right. So how do you describe the circle? Anything you have tried? What's the circle here? This cylinder here, Can we rewrite this cylinder equation? Right, how do we write this? S squared minus 2x plus y squared equals 0. Then plus 1 on both sides. Why? Because I can rewrite this into a circle equation. Okay, so by factorization, I'll get x minus 1 squared plus y squared equals to 1. So this means what? This is a circle centered at 1, 0 with radius 1. Okay. But there's no z here, right? This is the circle. There's no z. How do I draw the cylinder? It means that for all z, I have this circle. Okay, I have the same circle at OZ. So that's why I built the cylinder here. Okay, so you should imagine you have the surface. Something like this, right? Okay, and then you have a cylinder covering here. Okay, and then you want to find the volume bounded by what? Under the surface, inside the cylinder, under the surface. Okay, and then above XY plane. Okay, so meaning what? It is the surface. This is the volume above the circle under the surface. Okay, so it's equivalent to the volume above the circle, right? Circle of the cylinder, above it, and then under the surface. Does it make sense or not? So this picture here is equivalent to you draw a circle down there, and then you look at the surface under this, above the circle. Make sense or not? Does it make sense? Okay or not? So the intersection of the circle, you can think of a volume above the base circle and then under the surface. Okay. So you need to determine what's your D, what's your integration domain here. So it's picture like this. Okay. But because this is a polar rectangle, right? Okay. Remember, we have seen this picture before. Okay, we have seen this picture before. How we describe this using a polar function. Okay, it is just r equals to 2 cos theta. Okay, remember the first example we draw in a polar chapter, polar coordinate. So how do we describe this? The radius is going from 0 all the way to 2 cos theta. How about theta? Theta going from where to where? 0 to minus 0 to not 2 pi. Pi is enough. Okay, pi will draw everything. This is the first example we see last time. Okay. Up to pi is enough. You can try and plot it again if you forgot. Yeah. You can plug what is pi into here. And then what is 0? And then what is pi over 2? Okay. You can see that we managed to get everything on the circle. Okay? Okay, no? This is the very first example we draw in the polar coordinate chapter. Yeah. Before the limason. Still remember the limason? No? The snail. Yeah. Snail. Limason. Cardioid. Right. Yeah. Before that, we draw this shape. Okay, so let's set up our double integral. I managed to set up this double integral. Yeah. Okay, so we're going to use the polar coordinate here. Okay, so to use polar coordinate, my dA becomes r dr d theta. Okay, and then how about my integration domain here? So I fix my theta first from 0 to pi, and then my r from 0 to 2 cos theta. What is s squared plus y squared again? R squared. Okay, so we integrate over r cubed dr d theta. Okay. Yeah, so do this integration here. What should we get? This integration, I get r to the power 4 over 4 from 0 to 2 cos theta d theta. Okay, and then from here we get 16 cos to the power 4 theta over 4 d theta. But this one is power of cos again, right? So we need to use double angle formula again. Okay, so if you're gonna use double angle formula, what do you get? Get 4 times 1 plus cos 2 theta over 2 squared d theta, and then become 1 plus 2 cos 2 theta plus 1 plus cos 4 theta over 2 d theta. And then you are safe to go for integration. I'll get sine 2 theta plus theta over 2 plus sine 4 theta over 8 from 0 to pi. And then see what you get. See what you get. You get what do you get here? Hmm? 3 pi over 2. Okay, you should get 3 pi over 2. And you should get a pi plus pi over 2 here. Okay. Yeah. Okay. Any question about this general polar region here? It's similar to XY situation, right? Where you bound your theta and then your radius is changes depending on the theta. Okay. Of course, you could imagine you fix your R first and then you could change your theta as well. But just remember that when you integrate over polar coordinate, you need to have a radius factor. Okay, you need to multiply by a radius factor. Okay, any question about this? So in next session, we're going to triple integral. Okay, it's what I discussed just now. So there are 3 integral signs later. Okay. So let's take a break until 503. Okay, 503. Let's return 503. Don, have you decided your topic yet? Not yet. But you say you got the direction, right? 我要不要做？要不要换？哦，Why is that actually？你还没跟我讲。哎，那个 idea 是
他是要写，哎，我昨天要写的一点。
这个是我们就是很做的。还有一些你怎么付？这个是要往前，来了，对，只能把手，然后。但是我记得我当时还没有，下周跟我们年轻人一起打。
好吃了。
应该很麻是应该去玩。
对吗？有一点。所以我们周四会中午呢，你到时候拍比较好用。
干嘛？哦，OK OK。
对对对对，然后是什么？
不结合。
一样的。
给你一个思路，但是下面会跟对，我是对是得把那个还得调。
比如说，你看这个这个。
里面
也可以再给做这样一点，还有几分，再买一个点，就用到100啊，不是，两不是就在哪边？对。啊，运用这个生活。啊，几个小时，然后就可能他这个地方。 变化，所以你就可能在算，你有看 A 测嘛？你做这个嘛？
你们这么高，来，
啊，你如果拿这个东西到这个吵起来，这颜色会变，然后只要变都是这个条，它的机会高一点，好，就这样。啊，所以你用这一个这个 description 来 describe 那一个版本。几天这样到一回来的是那个，那是不是很饿？一了，吧，这有钱啊，还没给你钱。
然后我讲不要这件事。不要签什么给？只有一个对是对在里面，身上会给那个角色，对。
这一段就有点像这个你要讨论的。
讲的有钱是要去吃。这个话你说去，但是一看到特别好运气。
所以你算如果只要它随意可以，它不用在那个地方，我们会到处对你，对有关系的，对。哦，所以就是会表面嘛，对，他们都一样。是这个，所以可能你两个钱那个地方是在，这个是对的，是那个。
有来，
你可以他是用我
专是我
没错，网络是这么是会导不错情况。
这也就是
啊，因为写的是
顶我这也是当下面吗？
这样子我来马来香港人。
That's it. Okay, we continue. Let's continue. Okay, just now we skipped this part, right? So what is the integration over polar coordinates? So in rectangular coordinates, right, you use rectangle, okay? But in polar coordinate, you use polar rectangle. You still use rectangle, but you use polar rectangle. But polar rectangle will look something like this. Okay, it's no longer the rectangle like this. Okay, so you need to look at rectangle like this, something like this. Okay, and then you take the limit when this rectangle smaller and smaller and smaller. So previously you subdivide on x and y, but now you subdivide on angle and radius. Which way is which way? Where is radius? Where is okay, radius is this way. Okay, angle is this way. Okay, correct, right? Yeah, angle is this way. Okay, and then radius is this way. Okay, so you can see that one piece of rectangle is like this or square, but you see the polar rectangle here is like a squeeze square. I'm telling you where the R come from now. Here is a square. Square, you know, is just length times width. But rectangle here, you are like stretch. I mean, this paper, you see this paper, you stretch it. I cannot stretch it out because this will again. Yeah, I will break this paper. So you imagine you stretch this. Is you imagine you take a clay. What do you call it? Clay into okay. You can stretch it. Okay. The moment you stretch it, you will introduce the factor R here. Okay, you can see that this is not flat, not straight, right? Okay, so you introduce the factor R when you change variable here. Okay, so this is a geometric meaning. But still, I will do it formally later. Okay, don't worry. We will do it formally later. But the moral here is, you see, all side is straight here. But if you make it a polar rectangle, you kind of stretch it by a factor of R. This is the moral, but I will tell you the formal definition later. Okay, no? So why this R pops out? You can imagine that you have a rectangle get stretched into a polar rectangle. You can see that the two sides here is no longer straight. Okay, it's like part of the circle. The straight side here get elongated, and then this side also elongated. Okay, so the rectangle have a factor of. Okay. Okay, let's continue with triple. How about triple integral? Triple integral means what? 4D, hey, correct, 4D. Yes, my domain become three-dimensional. Okay, my domain become three-dimensional, and then my function should live in 4D. Okay, yes. Okay, so you see, my domain, so in calculus 1, your domain is what? It's just an interval. Okay, just an interval. Just now we learned double integral. My domain become surface. Or we start with boxes. Not box, square. Then the volume is the boxes. But now the domain become boxes. Domain itself is a box. I cannot draw the volume for you. If you can call, what are you computing? What we're computing is something in the textbook. It will call you a hypervolume. Okay, it's a hypervolume. Okay, it's no longer volume, it's a hypervolume. I don't know how to draw. If you know, please tell me. Call me immediately. If you know, please call me immediately how to draw. Okay, yeah. So the picture here is just domain picture. Okay, now it's not the graph, still domain here. Okay, then your double integral is similarly defined using the triply sum and the triply limit here. So you need to cut in the x direction, you need to cut in the z direction. Okay, z is like this, and then y direction. Okay, three direction you need to subdivide to get your hypersurface. Okay, so this is the definition, but of course we won't use this definition. Okay, and similarly we will have Fubini's theorem here. Okay, if your f is continuous at the box B, okay, we can do Fubini as well. Fubini says what? We can do the iterated integral, and then no matter how you do the order, they give you the same answer. Okay, this is from box. We're also starting from box first. Previously, we're starting from rectangle. Now we're starting from both. And then we will talk about general region similarly. Okay, so let's do this. Very quickly go through this. So I have B. What is B here? So B here is 3 coordinate x, y, z, and then S is an interval from 0 to 1. So let's draw it. Let's draw this stuff. So X, Y, and then I got the Z. Okay, so my X is going from 0 to 1. Okay, say this side here. Y is -1 to 2. Okay, so it's on this side here. So I spam a rectangle here. Okay, and then my height from 0 to 3. Okay, so all the way up to 3. So how to draw this? Like this. Okay, I think I know. So let's try this. Okay, I think I should draw the vertical line first. This, draw like this, and then like this, this. Okay, this one a bit. There's another color, make it clearer. So let me draw this line first. Okay, and then draw this line, and then draw this line, and then I draw this. Okay, then I draw too far away, a bit too far. So draw here, draw this. Okay, what's wrong with it? Shana, 3 more, huh? Move the 3 more. Okay, let's do it. So how about here? What do you mean? No? Like this. And then like this. And like this. And why not? Why not? You draw, I think I almost finished the box already. You try? Sorry. Okay. Sorry. Oh. Yeah, don't love it.
它这个的长度应该要跟这个有一样线。
Okay. Oh, copy paste. Yeah.
过来，这个，不要过来，你过来，差不多是这样子。
Also work. Also work. Okay, this way also work. Okay, this way also work. See you how to imagine this thing. Okay, so let me finish it like this, and then like this. Okay, and then to make it behind, look behind. So let me like this, like this. Okay, yeah. Okay, now can see the box. Hopefully you can see the box. The box is standing up like this, going this way, standing up. Okay, so this is the box. Okay, if it is the box, so you are computing the triple integral over a box. Then the Fubini tells you that you just do the iterated integral dx, dy, dz. Any way you like, you can do dy, dx, dz, dx, dz, dy, dz, ds, dy, dz, dy, dx. So I think there are 6 combinations, right? You can do any one you like. You should get the same answer. Can we skip this calculation or not? Let's just skip this calculation. You can try it. If you don't believe, you will get 27 over 4. Okay, yeah, just do integration over x. And then the other is a constant, and then you can keep doing it. Okay? Okay. So this is just an example, but the most important thing is about general region here. Okay, so what's about general region here? So first type of region looks like this. So you have the base shape. Okay, you have the base shape, but this base shape repeats. Okay, repeats for different z. Okay, the base shape repeats for different z. For example, what? For example, the cylinder. Okay, the cylinder. So what's the base shape for cylinder? Is the circle. And then all the disc, if we want to be solid, you take the disc and then you put a lot of this together. You form the cylinder. So this is the type 1. So meaning what? Meaning the height, the z, depend on your x and y. Okay, the z depend on your x and y. Okay, so that's why you have a double integral of domain, and then this domain here will control your height. Okay, this domain here will control your height. Okay, the domain here will control your height. Make sense, huh? Okay, let's go further. How about this one here? So for this, you will see that if you fix x, what happened? If you fix x here, this shape here, you can see that your y, you can write your y in terms of x. Okay, so if you fix x here, what happened to your y? Okay, your y is bounded below by this function and bounded above by this function. And then you repeat the shape again. Okay, okay or not? Does it make sense? You see, so how do you get this shape? How do you get this shape? Can you see that you have the same base shape across your height? Okay. And then if you just look at a single shape here, what happened? Okay. You can see that actually this is not quite accurate, but on this two sides should be fixed. I mean, it should be constant. Okay. Meaning what? Meaning if you fix an x, okay, then your top and the bottom limit is bounded by a function in x. Okay. This is just theory. Later we will see example how we cut these things out. So similarly, let's look at more example first. So how about this? How do you cut this shape? Where's the basic shape here? Where's the basic shape? Let's zoom in. Where's the basic shape? Where stay constant? See, so this side here is it's not constant. It's like going in. Actually, you can see from here. Right? But these two sides is constant. Okay. Okay, no? So meaning this side is what? This side is y. Okay, so if you fix y, then you can integrate over. If you fix y, you integrate over x. So these two functions, you should check. Is it depend on y or not? Okay, it depends on y. Okay, from h1y up to h2y. Okay, and then once you determine the domain, and then how you determine the height? So all the height here will be depend on what point you pick here. Okay, let's say if you pick this point here, where's the height? Okay, let's say you pick this point here. The height here is here. Okay. From this bottom plane to the above plane. Okay, if I pick the other point here in the domain, where's the height? It's in the middle of the shape, okay, or the region. Okay, now let's look at a few more examples. How about this example here? Where's the basic shape? Okay, basic shape is this D here. Then you can see that this part, so you can put the D and then you repeat a lot of D here. Okay. So meaning you need to determine your D first, and then you can determine your, in this case, it's not height anymore. Maybe it's a length. Okay. Yeah, I mean, we just flip the coordinate. Okay. How about this shape here? Where's the basic shape? Okay, you can see that you are repeating the D again. Okay, but in the different direction now. Just now we go in the X direction. Now you go in the Y direction. Okay. Okay. Okay, let's look at one example here. Okay, let's see how we apply this idea. So try and evaluate a function Z where the domain is this solid tetrahedron bounded by four plane x plus y plus z equals to 1. So this is a slanted plane. What's the normal of this plane? Normal. What's the normal of this plane? How to read the normal of x plus y plus z equals to 1? 1, 1, 1. 1, 1, 1. One, one, one. How to read the normal of a plane? A x minus a naught plus b y minus b naught plus c z minus c naught, right? Equals to 0. Right. So how to read this plane here? X minus plus y plus maybe z minus 1 equals 0. So what? So ABC is the normal vector to the plane. So what's the ABC in our case? 1, 1, 1. Okay. So where's the 1, 1, 1 vector? So 1 is here, x, and then 1 y is here, and then 1 up. So you need to move your vector up. So that's why this plane slanted like that. Make sense or not? 1, 1, 1 is going up here. Okay. Okay. Does it make sense? Make sense or not? Where's the 1, 1, 1 vector inside this graph? Facing where? Facing up. Okay, and facing out and then facing up. Okay, so that's why my plane slanted like that. Okay, because it's coming up. Okay. Okay, and then how about the other side? So s equals 0. Where is s equals 0? S equals 0 refer to which plane? YZ plane, correct. ZY plane. Okay, YZ plane. How about y equals 0? XZ plane, correct. And Z equals 0 refer to the XY plane. So XY plane is particularly easy to see because Z equals 0 meaning what? There's no height. There's no height, so it's the XY plane. Okay, so is this a solid tetrahedron? So we want to integrate this triple integral here, right? So you should imagine some hyper volume there, right? So this is just a domain, and then this domain will give you Z. So meaning what? If you take all these points, right, and then you sub into your function, this function only depend on Z. Okay, so what you can imagine is this is a solid tetrahedron. So every point here carry a number. Okay, carry a number, which is Z. For example, on the XY plane, there are this triangle here, all these points here, carry what number here? What's the number carried by this point? These are Z equal to 0, right? So the number they carry is 0. How about the point up here? What's the number it carries? 1. Okay, it carries 1. And then in the middle, they carry number in between 0 and 1. Okay, and then you can see that this tetrahedron, right? Try and slice it. Let's slice it horizontally. What do you get? You get the triangle getting smaller and smaller. Right? You get the triangle smaller and smaller until you get one dot. And then each triangle here carry a number. Each point on the triangle carries a number, which is the height. 0, 0.25 maybe, 0.5, 0.75, all the way up to 1. Okay. We don't know how to draw, but we know that they carry a number. Okay. This is a very crucial afterward about vector field stuff. Scalar field, vector field, scalar field. Okay. All right. So Fubini's, does the Fubini's tells you or not? Okay, Fubini's implies the general region. So how do we make this general region here? So similar to the two variable case, okay, you need to decide what is the interval for your x, what is the interval for your y, what is the interval for your z. Okay, we need to fix one direction. Which direction do we want to fix? X, Y, Z. Which direction you want to fix? Z first. Okay, let's fix Z first. Here I got prepared 6 method already. So we start with Z, okay, and then which one? Which do next? Y, X. Okay, let's do this. So Z. So let's think where Z go from where 0 up to 1. Okay. So when we fix Z, so this direction is fixed. So we need to see what's the domain you get here. So how about Y? Okay, what does Y depend on? So you see, at one point here, Y is going from 0 to 0. X is also going from 0 to 0. Okay, but let's pick another Z. Maybe pick this largest one, Z equal to 0. Okay, what happened to my Y? From 0 to 1. Okay, from 0 to 1. Let me see. Careful a bit. So my Z is from 0 to 1. Careful. So my, wait, let me think first. So let's be careful a bit. Let me see. You say that, okay. Sure. Let me tell you something. So let's say you want to fix this from 0 to 1. Let's see what's this picture give you. Okay. Y is from 0 to 1. Okay, let me move this guy here. So what's this picture? Do you know? Z from 0 to 1, Y from 0 to 1. This is supposed to give you a rectangle or square, yeah. Okay. In this case, it's square. So where is this square here? So where is this square? Z is from 0 to 1. Okay, Y is from 0 to 1 as well. So you get a square. But did you see square here? No, right? So what's What goes wrong? The square varies. So what should be the square then? What should be the region then? 0 to z minus 1, how do you determine that? Huh? Do you want to look at this guy? Look at this guy. Okay, look at this guy here. Okay, so what's this slanted line here? At this ZY plane, right? So when we want to determine y from z, we look at the ZY plane. Okay, so we look at the ZY plane here. So at ZY plane, what happened? Remember, ZY plane, x equals to 0. Okay, so this term here will reduce to what? This term will reduce to what? Z equals to 1 minus 1. Meaning y equals to 1 minus z. Okay, so actually here is 1 minus z. Right? Okay, now. So you look at how this line changed. Okay, you fix the z. Okay, and then see how the y changed. On which plane? ZY plane. Because we are not discussing about x yet. So we just look at the ZY plane. Okay, so the trick here is if you look at z first, you just look at the interval z. If you look at y in second, what do? You look at ZY plane. Okay, you look at ZY plane. All right, so we already settle this triangle here. But this picture is what? This picture is you need to cut your ZY plane in the x direction. Okay, you can see the rectangle going smaller in this way. Okay, so you are cutting differently than what I cut just now. So how do you cut it? So you cut in the ZY plane. Okay, so let me see. So you have this, and then like this, and then like this, and like this, and then all the way go to top. Okay, you are cutting it this way. So you should guess if I cut this way, which order I pick. Okay. So in the ZYS, you are picking this order here. Okay. So how does my S change then? Depend on the Z and Y. How does my Y change? How does my X change? Obviously, my S change from 0. Okay, starting from 0. This is quite obvious, right? But what is bounded by above by what? Bounded above by what? See how to make this triangle diminish. How to control this triangle? How to control this triangle getting smaller? Who is pushing this triangle smaller? Yeah, it's the x. But what's the surface that controls this triangle that getting smaller? Yeah, z equals to 1 minus x minus y. Because you have this surface that bound you. Right. This is the surface that bound you. So what do you get on the upper limit? One minus y minus z. Okay. You could try other value. Maybe you can try 1. What happened? You will get something like a you will get you will just get okay. Let's try. Let's change this value and then see what we get. Maybe you will have a better idea, right? So let me throw this. Let's do experiment. This is very important. This imagination for this chapter. Otherwise, you don't know how to change your variable. Okay. Let's determine a different set of value. So how about this? Can you imagine what's the picture for this set? So let's say we fix 1. Can you imagine what picture I should get here? So I have the same bounding variable for z and y. How about x? I fix a constant. First of all, the easiest case is all of them are constant. In that case, you just get a box. So once you introduce surface, right, you are like cutting the box in different way. Okay, you cutting the box. Okay, you cutting the box. But now I cut box in one way only, in the y direction. Okay, but I fix the other way. So what's the shape I should get here? Try and guess. Not guess, count it. I mean, calculate. Huh? 柱子 What 柱子 What's 柱子 Want to guess? What do you get? Huh? Yeah, you just get the not pyramid, but what do you call it? You just get a lot of triangle, not diminishing triangle. Then you join them together like this. Again, x from 0 to 1. Okay or not? You just repeat this, the first triangle. You keep repeating the first triangle. Okay. So you see, this triangle here is coming from a box, right? Can you imagine or not? Can you imagine this triangle coming from a box? Can you imagine this triangle coming from what box? What's the box it came from? What is the largest value you can get from 1 minus z? You can get 1. 1, right? Because 0 is in between, z is in between 0 and 1. So 1 minus z, the largest is 1. So what's this box here? So always remember first I mean, if you want to check your region is correct or not, start with the box first. Okay, so the box here is just the unique box, right? 1, 1, 1, 1 on every side. Correct or not? 1 on every side. Okay, so what happened to this triangle shape here? You just cut your box in the triangle direction. I cut this box diagonally. Make sense? Then how to go from this triangle go to here? You cut this triangle here. Can you call it diagonal or not? Yeah, I think you. How to say how to say this? Anyone can imagine or not? What are we doing? You can imagine, but can you describe it? Okay, so you take a plane. Okay, you take a plane. You try and slice it down here along this region up to here. Okay, let me draw it. So how to draw it? Challenging. Like this. Cut it like this. Okay, now you take a plane. You slice through this red line from here all the way into until you reach this top. Then you will slice to this tetrahedron. Make sense or not? And then what is this plane? This plane is exactly z equals to 1 minus x minus 1. Okay or not? You should imagine this is a 3D. You should imagine this is a 3D. Okay. To make it more 3D, maybe I make some dotted line here. Okay, to make it more 3D, let's make this dotted. Okay, and then what do you imagine? You imagine you slice a plane from this diagonal here all the way into until you reach this top. And then this is the solid tetrahedron you get in the first place. Okay, and then what's this plane? This plane is exactly the plane given by your question. X plus y plus z equals to 1. Okay or not? Any question? Any question on how to get this? So always the most simpler object is the box. Okay, from the box, and then you introduce a few variable such that you can cut this box into the object that you like. Make sense? Make sense or not? This chapter, the integration domain is harder than the integration itself. So you must get the integration domain right. Okay. Yeah. You see, integration is just on Z only, but the domain is like very complicated. Is this one? Okay. Okay or not? Any question on how to cut this? What time is it? Okay or not? Okay. So recap again. So what's the direction we are doing? We are doing Z, Y, X, D. So meaning is in the different order in the integral. So we do dz and then dy and then dx. Okay. So in other words, we look at the z direction first. Okay, let me draw a bigger picture. So we look at the z direction. We look at the z direction like this, going from where to where? 0 to 1. Okay. This is the z direction. Let's say here, 0 to 1. Yeah. Okay. And then we look at the zy direction. Okay, what happened to zy? Okay, if I pick z, what happened to my y? Meaning this is a zy plane. So you need to cut your surface at the zy plane. Remember that we get a triangle just now, right? Okay. And then it's bounded by 0 and then bounded above by this. What is this line here? How to get this line? This is y minus, so this is, okay, wait. So this is part of the surface of z equals to 1 minus x minus y. But here, my x is equal to 0. So this surface here go down to 1 minus y. Make sense or not? Because this is just a line. Because initially it is a plane. But I just look at this line here. So it become a line. Okay. So this is the zy plane. Then how about the if I compute all the directions, z, y, and then x. Okay, what's the shape here? So this is the shape that diminish that I draw just now. So you have a triangle here, but you can see that the triangle getting smaller, smaller, and smaller. Okay, smaller, smaller, and smaller. Okay, right. So you form this spectrum. Okay, does it make sense? Make sense or not? Okay. Okay. Very important, no? There are 6 directions here, right? You should try all the 6. What happening to all the 6? Okay. Let me see. Can I show you some picture now? For example, this picture here. Okay, I try to cut it in different way. So let's pick hey, actually I don't need to show you this one. I show you the one in my yeah, let me show you this. Okay, so let's change the order. Is this the order we use just now? Z, Y, X. This is the order we use. Okay, then we skip this. Okay, let's see, we pick dy, dx, dz. So dz, xy. Okay, what happened to z, xy? Similarly, z is from 0 to 1. Okay, it's the same. How about zx? What's the shape of zx here? Zx is still a triangle. Okay, so you need to draw your zx shape. Is this triangle here? Then you need to determine what's this bounded above by. So this is part of the plane again. But at this line here, y equals to 0. Okay, so this plane here is described by z equals to 1 minus x minus 0. Okay, which is 1 minus x. Okay, no? Okay, and then you need to consider z, x, y. Okay, what is this shape here? So I drew the tetrahedron here already. So the zx is on this side. Then we need to go to the y direction. So what happened? So what happened is the triangle diminish on the y direction here. Okay. And then how you control it? How do you control this diminish? It's still controlled by the plane. Okay, still controlled by the plane. Okay, still controlled by the plane. So you can see that the y value here is depending on bounded below by 0. Okay. And then how about these values here? These values here depend on y equals to minus x minus z. Okay. Yeah. Okay. So you can see that this y here is very dependent on x and z. Okay, so if you stare at different x, stare at different z, you have different y. Does that make sense or not? Can you see this orange line here? So if you have different x and z, so you should imagine this there's a z at the top. Okay, there's a zx here. Okay, and then zx here, on different zx, you will have different y. Okay, but the outermost y you can get is those on the plane. Yeah. Any question or not? Huh? No question. Let me see. Can I make this more concrete or not? Big things to say. Yeah. Okay. So I guess how should I? Yeah. Okay. See from here. Let's see. This is your tetrahedron, right? Okay. We will fix the zx plane first. Okay. And then you should imagine that every point here, every triangle here, there's a line shooting up. There's a ray coming up from that line. Okay. And then this ray, how long is this ray? The length of this ray is controlled by this plane here. Make sense or not? So okay, let me draw the picture for you. Okay, let me draw this last picture, and then we can go. Okay, so what does that y doing? What's the y doing? So the y is doing this. So every z and x, you have a controlling y like this. So you got y like this, 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 and then here like this, like this, like this, like this, like this, like this. But what's at the top here? Top here, it is just 0, 0 to 0. So there's only 1 point here. Okay, and then the other line you will get like this, like this, like this, something like that. Wait. So let me think. So I think I drew something weird here. Okay, let me draw something else first. Let me check the xz on this line, right? Okay, let me check the xz on this line. So it should be something like that. And then getting smaller, 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 smaller until you get this point. Okay. And then how about the y ray coming from this line here? Okay, how about that? How about this? Mm-hmm. How about that? Huh? Any idea or not? How about this line? So what have I made already? So I have made this triangle. I have made this triangle. How about those in between? 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 Can you imagine or not? Huh? Yeah. So what have I done? So what have I done is I have this piece, right? So help me again. So let imagine this. This one I got the ZX plane at the back. Okay. I just can you hold this? You sit here. You hold this. Yeah. This is the ZX plane. Okay. And then what is Y? What is Y here? Y here is all the line popping up from this. Okay. Okay. So for now on, I check this line and this line first. Okay, I check these two lines first, these two boundary line first. And then I found this Y ray here. So on the x-axis, I have some Y ray coming up. On the z-axis, I also have some ray coming up, like that. Make sense? But tetrahedron, I need to fill in the middle, right? So what kind of ray I need to have here? Okay, this is described by the equation of this Y, the upper limit of this Y. Okay, this, can you call this also? Yeah, and then for all the middle point here, this ray here will fill up the tetrahedron. Does that make sense? I just built the frame now. Then you need to fill the tetrahedron. Okay, you need to fill the tetrahedron. So here, the Y should be 0. And then slowly you grow. Then you can fill up the tetrahedron. Make sense? Does that make sense? Yeah. On this side, the Y is 0. And then when you go in, your Y will keep growing, until you fill the tetrahedron. Does it make sense? Does it make sense? Yeah. Okay. Okay or not? We will repeat the exercise again next time. Okay. Please go back and try different direction, and then see if you can draw it differently or not. These triangles. Okay. For this chapter, the integration domain is more important than the integration itself. Okay. If you get wrong integration domain, then your answer will never be correct. What's the answer? Have you tried? Should be 1/24. Because this thing is positive, right? Should be positive. Yes. It's 1/24. No matter which way. So if you pick different way, your integration domain should change slightly. For this case, it's slightly because it's symmetric from any side. Okay, so it's. We will see more example on this. Okay, and the example will get trickier. Okay, so please go back and try in different direction. I will post the different direction answer. Okay, yeah. Right. So go back, please also find your project, and then you can send me your presentation draft or project written draft also can. Okay. No need too long. No need too long. Just 0.5 page to 1 pages report, and then you should phrase your problem as a real life problem, and then solve it using calculus. Okay. Right. See you next Thursday. Hey. Yes. 应用吗？而